Hello there and welcome to the Sleepy Facts channel. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to the gentle pace of nature's slowest creatures rather than counting sheep. Either way, tonight's journey is for you. Let your mind relax, your breathing slow, and your body grow light, as if moving through thick honey. Because tonight, we're exploring the slowest animals on Earth. Creatures who have mastered the art of moving through life at a pace that makes urgency seem like a foreign concept. We'll drift from sloths hanging in rainforest canopies to snails, leaving silver trails across garden leaves, discovering how slowness itself becomes a survival strategy. Some of what you hear tonight may surprise you, or at least spark curiosity as you drift off. Before we begin, if this helps you unwind, consider liking and subscribing, one sleepy soul at a time. Now, let's begin. The three-toed sloth moves through the rainforest canopy at a maximum speed of roughly 13 feet per minute, making it one of the slowest mammals on Earth. This deliberate pace is not a limitation, but rather an adaptation that allows the sloth to conserve energy in an environment where food provides minimal calories. The sloth's diet consists almost entirely of leaves, which offer little nutritional value and require days to digest, meaning the animal must operate on an extremely tight energy budget. Moving slowly means burning fewer calories, and burning fewer calories means the sloth can survive on food that would starve most other mammals of similar size. The sloth hangs upside down from branches, its curved claws locked into the wood, barely moving for hours at a time. So still that algae grows in its fur, turning it slightly green and helping it blend with the leaves that surround it. Camouflaged not through speed or vigilance, but through the simple act of being patient as stone, the garden snail travels at an average speed of about 0.03 miles per hour, which translates to roughly 50 yards in a single hour of continuous movement. This pace results from the snail's method of locomotion, which involves waves of muscular contractions passing along its single foot, pushing against a layer of mucus that the snail secretes to reduce friction. The mucus itself requires energy to produce, and the undulating movement of the foot consumes energy as well, meaning the snail must balance the cost of movement against the benefits of reaching new food sources or suitable habitat. A snail crossing a garden might take an entire night to travel from one side to the other, leaving behind a silvery trail of dried mucus that marks its journey, a map written in slime that shows exactly where the snail has been and how long it took to get there. Each inch of trail representing minutes of slow muscular waves, patient persistence across distances that seem vast when measured in snail time rather than human time. The giant tortoise moves at speeds around 0.2 miles per hour when motivated, though much of its time is spent motionless, basking in sun or resting in shade. These tortoises, which can live well over 100 years, have evolved on islands where predators are few and food is abundant enough that rushing to find it serves no purpose. The tortoise's metabolism operates at a pace that matches its movement, slow and steady, allowing it to survive for months without food or water when necessary. Its shell provides complete protection from most threats, meaning the tortoise need not flee from danger, need not develop speed as a defensive strategy. The tortoise simply pulls its head and legs inside its shell and waits, patient and protected, until whatever threatened it loses interest and moves away. A giant tortoise might spend an entire day traveling just a few hundred yards, pausing frequently to nibble vegetation, to rest, to simply exist without urgency, its ancient eyes observing the world at a pace the world forgot was possible. Time moving differently when you measure your life in centuries rather than decades. The starfish moves across the ocean floor using hundreds of tiny tube feet, each one extending and contracting in coordinated waves that propel the animal forward at speeds rarely exceeding 6 inches per minute. This slow movement serves the starfish well, as it feeds primarily on stationary prey like clams and mussels that cannot escape regardless of how slowly the starfish approaches. The The starfish can also afford to move slowly because it possesses few natural predators and remarkable regenerative abilities, meaning even if something does attack it, the starfish can recover from injuries that would kill faster animals. A starfish might spend hours slowly advancing toward a mussel bed, its tube feet carrying it across rock and sand with the inevitability of tide, unhurried because nothing in its world requires hurry, hunting prey that cannot run, living in an environment where currents provide more movement than the starfish itself generates, drifting slightly with the water while its tube feet walk slowly along the bottom, patient as the stones it crosses, calm as the water that surrounds it. The koala spends up to 22 hours per day sleeping or resting motionless in eucalyptus trees, and even when awake, it moves with extreme deliberation, climbing slowly from branch to branch, at speeds that make sloths look energetic by comparison. This lethargy results from the koala's diet of eucalyptus leaves, which are toxic to most animals and provide minimal nutrition even to koalas who have evolved to digest them. The leaves contain compounds that require significant energy to detoxify, and they offer so few calories that koalas must conserve every possible bit of energy, turning slowness into survival strategy. A koala might spend 10 minutes climbing from one branch to another, just a few feet away, moving each limb with careful precision, never rushing, never wasting energy on unnecessary speed. The koala's brain is unusually small for a mammal of its size, another energy-saving adaptation, as brain tissue consumes significant calories even at rest. The koala thinks slowly, moves slowly, lives slowly, its entire existence calibrated to extract life from leaves that should not support life at all, managing this impossible task through the simple expedient of doing everything as slowly as possible, making each calorie stretch as far as it can. The sea cucumber lies on the ocean floor or buried in sediment, sometimes remaining motionless for days before moving to a new location. When it does move, it travels at speeds around 6 feet per hour, using small tube feet similar to those of its starfish relatives. The sea cucumber feeds on organic particles in the sediment, processing vast amounts of sand or mud to extract the small amount of nutrition available, a feeding strategy that requires no speed whatsoever. The animal is essentially a mobile digestive system, taking in substrate at one end and expelling processed material at the other, slowly working its way across the ocean floor, recycling nutrients and aerating sediment as it goes. A sea cucumber might spend its entire life within an area of just a few square yards, moving in slow spirals or lines dictated by the distribution of food in the sediment, never traveling far, because far is unnecessary, when food exists everywhere beneath you, only requiring the patience to process it, slowly enough that every available nutrient gets extracted, time abundant when you live in an environment where seasons mean little and temperature rarely changes, where the slow passage of years matters less than the steady accumulation of tiny meals, grain by grain, day by day, moving through sediment, the way glaciers move through mountains, reshaping the landscape through patient presence rather than forceful action. The Gila monster, a venomous lizard native to the southwestern United States and Mexico, moves with characteristic sluggishness, traveling at maximum speeds around 1 mile per hour, and often moving much slower than that. This slowness partly results from the lizard's low metabolism, which allows it to survive for months between meals by storing fat in its thick tail. The Gila monster hunts by scent rather than sight, tracking prey slowly and methodically, spending hours following scent trails to nests of eggs or young animals. Once it finds food, the lizard can consume enough to sustain itself for weeks or months, making frequent feeding unnecessary and therefore making speed unnecessary as well. The Gila monster spends most of its time underground in burrows, avoiding the desert heat and conserving energy, emerging only when conditions are suitable and food is available. When it does walk across the desert surface, it moves with a swaying gait that seems almost meditative, legs moving one at a time in deliberate sequence, body swaying slightly with each step, tail dragging across sand, leaving tracks that show how slowly it traveled, how much time elapsed between each footfall. The lizard unconcerned with speed, because its venom means it need not chase prey, and its armor of beaded scales means few predators bother to attack it, leaving it free to move at whatever pace suits its internal clock, which ticks slowly, measuring time in long intervals between meals, between active periods, between breaths that come slow and deep, filling lungs that rarely need to work hard, because everything about the Gila monster happens slowly, deliberately, with the patience of desert stones warming in Sunday. The slow loris moves through forest canopy with such deliberation that its motion becomes almost invisible. Each limb placement carefully tested before weight shifts, each movement flowing so gradually into the next that observers sometimes cannot determine whether the loris is moving or simply swaying with branch movement in the breeze. This extraordinary slowness serves as camouflage, making the loris difficult for predators to detect. As most predators key on movement to identify prey, the slow loris can freeze mid-motion and remain perfectly still for extended periods, holding positions that would exhaust more active animals within minutes. The loris hunts insects, tree sap, and other small food items that require careful approach rather than speed. And its toxic bite, delivered through grooved teeth that channel venom produced in glands near the elbows, means it need not flee from many potential threats. The loris moves through the night like liquid in slow motion, arms and legs extending and contracting with glacial patience, eyes huge in its small face, reflecting what little light penetrates the canopy, watching for food, watching for danger, watching without hurry, because hurry serves no purpose. When your survival depends on not being noticed, on blending into the moving shadows of leaves stirred by wind, on becoming part of the branch rather than an animal traveling along it, existence as stillness with direction, movement as an extended freeze that happens to result in position change over time. Measured in minutes, per foot, per yard, per tree, the slow loris embodying patience so complete, it transcends patience and becomes something more like inevitability. Arriving eventually at every destination, reaching eventually every branch worth reaching, surviving through the simple strategy of moving too slowly for danger to notice, too gradually for prey to recognize approach until too late, slowness as both camouflage and weapon, defense and offense, entire survival strategy compressed into the art of moving, as if time has different meaning, as if the urgency that drives other creatures is optional, an artifact of biology that the slow loris has chosen to disregard, building a life from patience and poison, and eyes that watch the world without blinking, without hurrying, without concern for how long anything takes. Because time, for the slow loris, is abundant beyond measure. The manatee glides through coastal waters and rivers at an average speed of about 3 to 5 miles per hour, though it can achieve brief bursts of up to 15 miles per hour when startled. These gentle marine mammals, sometimes called sea cows, spend most of their time feeding on aquatic vegetation, consuming up to 10% of their body weight daily, which for a half-ton animal represents a substantial amount of grazing. The manatee's slow metabolism and lack of blubber mean it must remain in warm water, restricting its range and making energy conservation important. The manatee surfaces every few minutes to breathe, rising slowly to take air, then sinking back down to continue feeding, moving through water with the calm of a creature that has few natural predators and no need to rush. Watching a manatee graze resembles watching a very large, very peaceful underwater cow. Its whiskered snout pulling up vegetation with methodical thoroughness, its paddle-shaped tail propelling it forward with lazy sweeps, its flippers steering it around obstacles with minimal effort. The manatee exists in a state of perpetual calm, disturbed only when boats approach too quickly, when cold water forces it to seek warmth, when something external imposes urgency on a creature designed for patience. In their natural state, manatees drift and graze and rest, occasionally socializing with other manatees in slow, gentle interactions that involve no aggression, No competition, just shared space and mutual tolerance. Creatures so mild that their greatest threat comes not from nature, but from the propellers of boats moving too fast through their slow-moving world. Speed meeting slowness with tragic results. Reminder that not everything moves at the same pace, and the slow have rights that the fast sometimes forget to honor. The banana slug moves through Pacific Northwest forests at speeds similar to garden snails, leaving trails of slime that serve multiple purposes beyond lubrication. The slime contains both a natural anesthetic that numbs the mouths of potential predators and pheromones that help banana slugs find mates. These slugs, which can grow up to 10 inches long and display bright yellow coloring that warns predators of their unpleasant taste, spend their time feeding on decomposing plant matter, mushrooms, and animal droppings, helping to recycle nutrients in the forest ecosystem. A banana slug might spend an entire day traveling from one side of a fallen log to the other, grazing as it goes, processing dead wood and fungus into forms more easily accessed by other decomposers. The slug's slowness means it never travels far from its birth location, usually remaining within a few hundred yards throughout its entire life, which can span several years. This limited range works because the forest floor provides abundant food, and the slug's distasteful nature protects it from most predators. The banana slug moves through its world like a slow yellow ribbon, bending around obstacles, flowing over bark and leaves and stones, forever damp, forever slow, forever processing the detritus of the forest into soil that will feed the trees that drop the leaves that become the detritus. The slug will eventually process a cycle as slow as the slug itself, turning over season by season, year by year. The slug patient participant in transformation that requires patience, decomposition happening at the speed of slime trailing across bark, at the speed of digestive enzymes breaking down cellulose, at the speed of nutrients returning to soil, slow as the growth of trees, slow as the fall of rain, slow as the turning of seasons in temperate forests, where banana slugs write their trails across every surface, mapping the forest floor in slime and time. The sloth's fur grows in the opposite direction from most mammals, with each hair pointing from belly toward back, an adaptation that allows rain to run off efficiently when the sloth hangs upside down. This fur hosts an entire ecosystem of algae, moths, beetles, and other organisms that live nowhere else, creating what amounts to a mobile habitat slowly traveling through the rainforest. The algae provide some nutrition, as sloths occasionally groom themselves and ingest the algae along with any insects living in the fur. The greenish tint the algae provide enhances the sloth's camouflage, helping it blend with the foliage where it spends its life. A sloth might host dozens of individual moths in its fur, moths that lay their eggs in the sloth's droppings when it descends to the forest floor to defecate, which it does roughly once per week, always at the base of the same tree. This weekly descent represents the most dangerous time in a sloth's life, as it must leave the safety of the canopy and become vulnerable to ground predators. Yet, sloths consistently perform this ritual, rather than simply dropping feces from the branches. The reason for this behavior remains debated, but it might relate to the moths, as moths that lay eggs in sloth dung eventually emerge and fly up to join the sloth in the canopy, completing a cycle that benefits both moths and sloths, the moths gaining breeding sites and the sloths gaining moths that die in the fur and decompose, providing nutrients for algae that feed the sloth. The entire system operates at sloth speed, cycles measured in weeks rather than days, partnerships built on slowness, on patience, on the willingness of multiple species to exist together at a pace that allows such intricate relationships to develop and persist. The giant Galapagos tortoise's slow metabolism allows it to survive up to a year without food or water, an adaptation that proved crucial during the age of sailing ships, when sailors collected these tortoises and stored them alive in ship holds as a source of fresh meat on long voyages. The tortoise's ability to survive without food made them valuable, and the tortoise's slowness made them easy to capture, nearly leading to extinction before conservation efforts established protected populations. Today, these tortoises live on islands where they face few threats, grazing on vegetation, basking in volcanic soil, and occasionally visiting mud wallows where they soak for hours. Different subspecies evolved on different islands, each developing slightly different shell shapes and sizes based on available food sources and terrain. Some subspecies have dome-shaped shells suited for lowland grazing, while others have saddle-shaped shells that allow them to extend their necks upward to reach higher vegetation. Despite these variations, all Galapagos tortoises share profound slowness, their lives unfolding over more than a century for successful individuals, reaching sexual maturity only after 20 to 25 years, reproducing slowly throughout their long lives, never hurrying, never rushing, simply existing at the pace evolution determined was sufficient for survival. On islands with plenty of food, plenty of space, and very few predators beyond the humans who nearly eliminated them, but now work to preserve the remaining populations, protecting the right of these ancient creatures to continue their slow progress through lives that span human generations. Witnesses to change happening around them faster than they could ever move themselves, islands transforming, while tortoises graze with the same patience they possessed. A century ago, 2 centuries ago, patience encoded so deeply in their biology that even environmental change cannot make them hurry. The sea anemone, despite being an animal, remains anchored to rocks or other substrate, moving only rarely and only slowly when it does move. An anemone might travel just a few inches per day by releasing its grip on one location and using its muscular foot to creep to a new position. This movement happens so slowly that observers watching for just minutes would see no change whatsoever. The anemone feeds by extending tentacles into the current, waiting for small fish, shrimp, or other prey to brush against the stinging cells, called nematocysts, that cover each tentacle. The anemone does not hunt or pursue. It simply waits with tentacles extended, sometimes for days, until something edible makes contact. Once prey is captured, the tentacles slowly contract, pulling food toward the central mouth, where it will be slowly consumed and slowly digested over hours or days. An anemone can live for decades in the same spot, perhaps moving occasionally to follow light or current, or the gradual shifting of the reef around it, but essentially remaining a fixture, a living flower that happens to be an animal, rooted and patient, feeding on whatever chance brings within reach, surviving through pure patience, through the willingness to remain in one place and trust that the ocean will eventually deliver food, as it always has, as it always will. The anemone, requiring only the ability to wait, to remain, to exist in stillness punctuated by the slow waving of tentacles in current, colors bright or drab depending on species, shapes various but always symmetric, always circular, always pat, embodying a form of animal existence so different from mammals that it barely seems to qualify as the same category of life. Yet, anemones are animals. They eat, they grow, they reproduce, they respond to stimuli. They simply do all these things while barely moving, while remaining essentially fixed in space, their lives unfolding not through travel or exploration but through experience of a single location over time, becoming experts in one small piece of reef, one particular rock, knowing it intimately through years of contact, through the seasons that bring different currents, different prey, different temperatures. The anemone adapting to these changes without moving, without fleeing, without seeking better conditions elsewhere, simply adjusting to whatever happens at this particular spot, committed to place in ways mobile animals cannot comprehend, slowness taken to its logical conclusion, which is choosing to stop moving almost entirely and let the world come to you instead. The North American wood turtle moves at roughly 0.2 miles per hour when actively traveling, though it spends much of its time stationary, basking, or hiding. These turtles, which can live 50 years or more, split their time between aquatic and terrestrial habitats, moving between streams and nearby forests depending on season and activity. In spring, wood turtles search for mates, males following females, and performing courtship displays that involve slow head bobbing and gentle nibbling. In summer, they range through forests, feeding on berries, mushrooms, insects, and plants, traveling surprisingly long distances for such slow animals, sometimes covering several hundred yards in a day of steady walking. The wood turtle's slow pace means it remains vulnerable to predators, especially as a hatchling, but its hard shell protects adults from most threats. The turtle's navigation abilities allow it to return to the same nesting sites and hibernation locations year after year, suggesting sophisticated mental maps, despite moving through these territories at walking speed or slower. A wood turtle might spend an afternoon traveling from its stream to a berry patch it remembers from previous years, walking with steady determination, stopping occasionally to eat or rest, eventually arriving at its destination hours later, the journey itself unhurried, the destination reached through persistence rather than speed. The turtle pauses at obstacles, considers routes around them, makes decisions with the same deliberation that characterizes all its movements, never rushed, never panicked, processing its environment at the speed of thought, which, for a turtle, might be slow by mammalian standards, but perfectly adequate for the pace at which turtles live, the world moving slowly enough that slow thinking suffices. Slow movement suffices. Slow everything suffices because the wood turtle lives in a time stream that flows at turtle speed, where urgency is rare and patience is the default state, where problems can be thought through carefully because thinking carefully takes time, and time is what turtles have. Decades of it, enough time to learn the forest, to remember the berry patches, to return each year to familiar places, building a life from slow accumulation of experience, slow growth of knowledge, slow addition of years until a long life has been lived, slowly and completely, without rushing, without missing details that faster creatures overlook. The thorny devil, a lizard native to Australian deserts, moves in a peculiar stop-and-go fashion, taking a few slow steps then freezing for several seconds before moving again. This jerky movement mimics the swaying of vegetation in the breeze, helping the lizard avoid detection by predators. The thorny devil feeds exclusively on ants, lapping them up with a sticky tongue at rates of up to 45 ants per minute, which might seem fast until you consider that the lizard must consume thousands of ants daily to meet its energy needs, meaning it spends hours at ant trails, slowly working its way along the line of ants, stopping frequently, moving with the characteristic freeze-walk-freeze pattern that defines its locomotion. The lizard's body is covered in sharp spines that deter predators, and its skin contains microscopic channels that draw water toward its mouth through capillary action, allowing the thorny devil to drink from dew or rain that collects on its body. These adaptations mean the lizard need not move quickly to find water or escape danger. Its defense is effective enough that slowness poses no significant risk. A thorny devil might spend an entire day traveling just a few hundred feet between ant colonies, pausing at each colony to feed until satisfied, then moving to the next source. The lizard's world consists of sand, spinifex, grass, ant trails, and time, all experienced at a pace that allows thorough examination of each ant trail, complete consumption of available ants before moving on, and minimal energy expenditure for travel. The thorny devil walks the desert like a living cactus, spiky and slow, occasionally rocking slightly as if moved by wind, occasionally darting its tongue to catch ants, mostly remaining still, patient, waiting for the heat to pass, for clouds to provide temporary relief, for night to come and bring coolness that makes movement slightly less costly, though even then the lizard maintains its slow, deliberate pace, measuring progress in yards per hour rather than miles, content to remain a small, slow presence in a landscape of heat and time. The seahorse drifts through seagrass beds and coral reefs at speeds around 5 feet per hour, making it one of the slowest fish in the ocean. This extreme slowness results from the seahorse's unusual body structure, which lacks the streamlined shape and powerful tail that most fish use for swimming. Instead, the seahorse swims upright, propelling itself with rapid oscillations of a small dorsal fin, while using even smaller pectoral fins for steering. Despite beating its dorsal fin up to 35 times per second, the seahorse barely moves, the tiny fin creating only minimal propulsion. The seahorse feeds on small crustaceans, approaching prey by drifting slowly closer, then suddenly extending its tubular snout to suck in food. This ambush strategy works because the seahorse's slow approach does not trigger prey's escape responses, allowing the seahorse to drift close enough for its strike. Seahorses anchor themselves to vegetation using prehensile tails, allowing them to remain stationary while they wait for prey to drift past, a strategy that conserves energy and suits their limited swimming abilities. A seahorse might spend days in the same small area, anchored to the same piece of seagrass, waiting for food, occasionally drifting to a new anchoring spot, if current or food availability suggests it would be advantageous. Male seahorses famously carry developing young in a brood pouch, providing protection and nutrients until the miniature seahorses are ready to emerge and begin their own slow journeys through underwater meadows. The entire seahorse life cycle happens at reduced speed, growth slow, movement slow. Even courtship involving slow synchronized dances, where mated pairs drift together through the water, tails linked, bodies swaying in unison, a display of togetherness that happens too slowly to seem like much motion at all, yet carries meaning for the seahorses involved, strengthening pair bonds that last season after season. Two slow creatures choosing to be slow together, swimming side by side at speeds that barely qualify as swimming, existing in partnership at the pace evolution granted them, slow but sufficient, barely moving, but moving enough, alive in waters that flow past them faster than they can swim, accepting that limitation and building a life within it, proving that even the slowest fish can find success if slowness is built into every aspect of survival strategy. The sloth's digestion takes up to 30 days to process a stomach full of leaves, making it one of the slowest digestive systems in the animal kingdom. This sluggish digestion reflects the low nutritional value of the leaves and the sloth's low metabolic rate, each factor reinforcing the other. The sloth's multi-chambered stomach hosts bacteria that help break down cellulose, similar to the digestive systems of cows and other ruminants, but the sloth's stomach operates at lower temperatures due to the sloth's low body temperature, which varies more than most mammals and can drop several degrees at night. Lower stomach temperature means slower bacterial action, which means slower digestion, which means food sits in the stomach for weeks, fermentating gradually, nutrients extracted slowly and completely, because the sloth cannot afford to waste anything. A sloth's stomach can account for up to 30% of its body weight when full, meaning the animal carries substantial weight from undigested food, yet another reason why moving quickly would be energetically expensive. The sloth essentially lives as a mobile fermentation chamber, hosting bacteria that slowly convert leaves to usable nutrients, while the sloth hangs in the canopy, barely moving, digesting through patience and time and bacterial partnership. This slow digestion determines the sloth's once-weekly defecation schedule, as the animal needs that much time to process a meal completely, to extract every possible nutrient, to reduce leaves to waste material that can finally be expelled. The entire process happens on a schedule measured in weeks, meals consumed slowly, digested slowly, eliminated slowly. The sloth's internal clock, running at a pace that would frustrate any faster animal, but suits the sloth perfectly. Time abundant when your entire life is slow, when weeks seem reasonable for digestion because weeks seem reasonable for everything. The American woodcock probes soft soil for earthworms, walking slowly through fields and forests, with a characteristic rocking motion that makes the bird appear to be doing a slow-motion dance. This rocking behavior serves multiple purposes, including potentially imitating rainfall on leaves, which might encourage earthworms to surface, making them easier to catch. The woodcock walks carefully, placing each foot with deliberation, pausing frequently to probe the ground with its long bill, feeling for the vibrations and textures that indicate worm presence. When the woodcock detects a worm, it extracts it by opening just the tip of its bill, while the bill remains inserted in soil, a flexible bill tip that allows the bird to grasp prey underground. The woodcock's eyes position far back on its head, providing nearly 360-degree vision that helps the bird watch for predators, while its attention focuses downward on feeding. This eye placement means the woodcock can see behind itself without turning its head, an advantage for a bird that spends so much time with its bill in the ground. The woodcock's slow, careful hunting technique suits the patient nature of earthworm hunting, where success comes from thorough coverage of good habitat, rather than quick strikes. A woodcock might spend hours working a small area, probing every few inches, walking in slow zigzags that ensure complete coverage, missing no spots where worms might hide. The bird's camouflage coloring makes it nearly invisible against leaf litter, and its tendency to freeze when approached means predators often pass within feet, without noticing the motionless woodcock pressed against the ground. The woodcock's slowness is selective, slow when feeding or hiding, capable of explosive flight when finally flushed, but spending most of its life in slow mode, walking deliberately, probing patiently, existing at a pace that suits a bird designed for patient extraction of hidden prey from soft earth. Time spent in slow search, rewarded with meals of earthworms, the woodcock's world consisting of steps and probes, and the slow accumulation of worms until hunger is satisfied and the bird can rest, standing motionless in undergrowth, digesting slowly, waiting for hunger to return, and the slow dance of feeding to begin again. The glass lizard, despite its name, is actually a legless lizard rather than a snake, distinguished by movable eyelids and external ear openings. These lizards move slowly compared to snakes, lacking the efficient locomotion methods snakes developed. A glass lizard travels by lateral undulation, similar to snake movement, but less refined, resulting in slower speeds and more energy expenditure per distance covered. The lizard spends much time underground or under leaf litter, emerging to hunt insects and other small prey using a slow stalking approach. When threatened, glass lizards sometimes break off their tails, which can account for up to 2/3 of the animal's length, leaving the severed tail thrashing on the ground while the lizard slowly makes its escape. This autotomy gives the lizard its glass name, as it appears to shatter like glass when handled roughly, though what actually happens is controlled tail release at predetermined breaking points along the vertebrae. The lizard can regenerate the lost tail, though the replacement never quite matches the original. A glass lizard might spend months regrowing a tail after an escape, energy diverted from growth or reproduction to reconstruction, a cost the lizard accepts as preferable to death. The slow growth of the replacement tail mirrors the slow pace of the lizard's entire life. Development proceeding gradually, maturity reached slowly, lifespan potentially extending decades for individuals that avoid predation. Glass lizards hunt by slow approach, taking minutes to creep within striking distance of prey, then lunging in a movement faster than their normal locomotion, but still not particularly quick by predator standards. The lizard succeeds because its prey consists of animals even slower than itself, or animals that fail to recognize the slow-moving lizard as a threat until too late. The glass lizard exists in a world where slowness works, because everything relevant operates at similar speeds, where being faster than your food matters more than being fast in absolute terms, where patient stalking combined with protective behaviors like tail autotomy and hiding provide sufficient survival tools that the lizard persists across much of North America. Common but rarely seen, slow but successful, living proof that speed is relative, and survival goes to those adequately adapted to their niche, rather than those who excel at any particular trait in isolation. The loggerhead sea turtle swims through ocean waters at cruising speeds around 1 to 2 miles per hour, though it can achieve bursts of 15 miles per hour when necessary. These ancient reptiles, which can live 80 years or more, spend almost their entire lives at sea, females returning to land only to nest. The turtles migrate thousands of miles between feeding grounds and nesting beaches, journeys that take months to complete at turtle swimming speeds. A loggerhead might travel from feeding areas off the coast of Virginia to nesting beaches in Florida, a journey of several hundred miles covered at steady, unhurried pace, the turtle navigating using Earth's magnetic field, celestial cues, and possibly other sensory information we do not fully understand. The turtle pauses to feed, to rest, to drift, with favorable currents, in no particular hurry, because it makes this journey repeatedly throughout its life, and has learned that steady progress reaches destinations just as surely as speed while costing less energy. Loggerheads feed primarily on jellyfish, crabs, and other invertebrates, food that does not require fast swimming to catch, allowing the turtle to maintain its slow pace while still meeting nutritional needs. The turtle's hard shell protects it from most predators once it reaches adult size, meaning the turtle need not flee from threats, need not develop speed as a defensive strategy. A loggerhead drifts through the ocean like a small submarine, flippers pulling slowly through water, head occasionally extending to snap at a drifting jellyfish, then withdrawing into the shell's protection, the turtle continuing its slow swim across hundreds or thousands of miles. Patient traveler in an ocean that supports patience, current and time sufficient to move turtles where they need to go. Speed unnecessary, when migration timelines stretch across months and navigation skills ensure eventual arrival at correct destinations. The turtle, knowing somehow that this pace works, has always worked, will continue to work as long as the ocean remains as it has been. Currents flowing, beaches waiting, time abundant for creatures who measure their lives in decades and their migrations in seasons. Slow crossing of vast distances, accomplished through persistence, through the simple act of continuing, of swimming another day, another week, another month, until the destination appears on the horizon and the slow journey ends, where it was always meant to end, at a beach remembered from previous visits. A beach that smells right, feels right, calls to the turtle in ways we cannot fully understand, but must respect, must protect, must allow to continue because these slow migrations, these patient journeys, these ancient patterns predate human civilization and carry within them knowledge of the ocean that we are only beginning to appreciate. Wisdom written in turtle navigation, in turtle persistence, in turtle slowness, that covers continents at speeds that seem inadequate, until you realize they have been adequate for millions of years, and the turtles continue, slow and steady, through waters we have changed in ways that make their slowness suddenly vulnerable, their patience suddenly threatened, their ancient pattern suddenly interrupted by challenges evolution did not prepare them to face. The lunar moth caterpillar feeds on leaves with methodical thoroughness, growing slowly through 5 larval stages called instars over the course of several weeks. Each instar requires molting, shedding the old skin to allow for growth. And between molts, the caterpillar feeds steadily, consuming leaf after leaf, at a pace that seems leisurely but ultimately results in substantial growth. The caterpillar moves slowly along branches, searching for the perfect leaf, then settles in to feed, mandibles chewing steadily, severing plant tissue in small bites that gradually consume the leaf from edge inward. The caterpillar might spend an entire day on a single leaf, or move between several leaves if the first proves unsatisfactory. This slow, thorough feeding continues until the caterpillar reaches full size, about 3 inches long, at which point it begins searching for a suitable place to form a cocoon. The cocoon construction itself takes many hours, the caterpillar spinning silk into a protective envelope suspended from a branch. Inside this cocoon, the transformation from caterpillar to moth proceeds slowly, taking several weeks as the caterpillar's body essentially dissolves and reforms into adult moth structure. The pupa inside the cocoon does not move, does not feed, simply exists in suspended development while transformation proceeds according to biochemical timelines that cannot be rushed. Eventually, the adult moth emerges, dries its wings, and begins its brief adult life, which lasts only about a week and involves no feeding, as adult lunar moths possess no mouthparts. The moth's entire existence serves reproduction, finding mates in the darkness, guided by pheromones, laying eggs that will become the next generation of slow-feeding caterpillars. The cycle repeats. Slow growth followed by slow transformation, followed by brief adult activity, followed by death. Everything in its time. Nothing rushed. The lunar moth's life history, built around periods of slowness, punctuated by crucial moments of faster activity. But even those faster moments barely qualifying as fast compared to many other insects, the lunar moth's entire existence operating at reduced pace, leisurely compared to the frenetic activity of flies or bees, calm and measured even in moments of urgency, the caterpillar taking weeks where other caterpillars take days, the moth living days where other moths live weeks, everything compressed or extended depending on perspective. But from the lunar moth's perspective, everything proceeds at exactly the right pace. The pace encoded in genes, the pace sufficient for survival and reproduction, the pace that works. The hagfish, sometimes called slime eels, though they are neither true eels nor particularly slimy under normal circumstances, moves through deep ocean waters at speeds rarely exceeding half a mile per hour. These primitive fish lack jaws and feed primarily on dead or dying animals that sink to the ocean floor, a scavenging lifestyle that requires no speed whatsoever. The hagfish locates food by smell, following chemical gradients through the dark water until it encounters a carcass, then burrowing into the body to feed from the inside out. This feeding strategy takes hours or days depending on the size of the carcass. The hagfish working slowly and methodically, consuming what it can before other scavengers arrive, or the food becomes too degraded to eat. When threatened, hagfish produce extraordinary amounts of slime from glands along their bodies. Slime that expands to many times its original volume when mixed with seawater, creating a choking cloud that deters predators. The hagfish then ties its body into a knot and slides the knot from tail to head, scraping off the slime and freeing itself to swim away. This escape happens in slow motion compared to most fish. The hagfish's movement almost leisurely, even in moments of danger, confident that its slime defense provides adequate protection without requiring rapid flight. A hagfish might spend weeks in the same general area of ocean floor, moving slowly between food sources, occasionally resting in mud or under rocks, existing at the bottom of the food chain where speed provides no advantage and scavenging patience provides everything. The hagfish's body plan has remained essentially unchanged for 300 million years, suggesting that their slow, simple lifestyle works so well that evolution found no reason to modify it. No pressure to develop speed or complexity beyond what already exists. The hagfish, perfect in their simplicity, adequate in their slowness, successful in their patience, ancient lineage persisting through time, measured in epochs while they move through water, measured in feet per hour, slow but eternal, simple but effective, primitive, but precisely what deep ocean scavenging requires. The garden snail's mucus trail serves purposes beyond locomotion, providing a chemical signature that other snails can detect and follow, allowing snails to find potential mates. Despite their slow movement and poor vision, a snail might follow another snail's trail for hours, slowly tracking the chemical signature across gardens or forests, eventually catching up to the trail maker and initiating courtship. Snail mating involves elaborate rituals that can last hours, including the exchange of calcium-rich love darts that pierce each partner's skin and deliver hormones that increase reproductive success. After mating, snails lay eggs in carefully chosen locations, usually in damp soil where the eggs will remain moist during development. The eggs hatch after several weeks, releasing miniature snails that begin their slow lives following the same patterns as their parents, grazing on vegetation, leaving mucus trails, moving at speeds that make progress nearly invisible to casual observers. A baby snail might spend its entire first year within just a few yards of its hatching location, gradually exploring outward as it grows, learning its territory through slow, thorough investigation that leaves no stone unturned, no leaf unexamined, building complete knowledge of a very small area rather than superficial knowledge of a large range. This intimate familiarity with local habitat serves the snail well, allowing it to find food efficiently, locate suitable shelter from heat or cold, and avoid the few dangers that threaten creatures protected by hard shells and distasteful slime. The snail's life unfolds slowly, years passing while the snail remains in roughly the same area, growing gradually, reproducing occasionally, surviving through the simple expedient of being too slow to get into trouble, too protected to fear most predators, too patient to exhaust itself through unnecessary activity, existing in a state of perpetual, unhurried presence that defines what it means to live as a snail, time abundant, space limited, life contained within boundaries measured in yards, experienced at speeds measured in inches per minute, yet full in ways that faster animals might not appreciate, complete in ways that speed cannot enhance. The snail's slow world, sufficient unto itself, requiring nothing more than what slowness provides. The West Indian manatee's closest living relatives are elephants, a relationship that seems unlikely until you consider that both lineages descended from the same ancient ancestor, and both retain certain features including continuously growing teeth that move forward in the jaw throughout life, replacing worn teeth at the front. This tooth replacement happens slowly, over years, each tooth gradually migrating from back to front as the animal ages and the front teeth wear down from grinding vegetation. The manatee uses this dental conveyor belt to maintain functional teeth, despite eating abrasive aquatic plants that would quickly wear down a fixed set of teeth. This slow tooth replacement mirrors the manatee's slow life history more broadly, with females not reaching sexual maturity until age 5 or later, producing single calves after year-long pregnancies, then waiting 2 to 5 years before reproducing again. Manatee calves remain with their mothers for up to 2 years, learning where to find food, where warm water refuges exist during cold weather, and how to navigate the waterways that will become their home ranges. This extended childhood allows for thorough education in the slow-paced skills that manatee survival requires. Mother and calf drifting together through seagrass beds, the calf watching and imitating, learning through repeated observation at speeds that allow complete understanding. Young manatees grow slowly, taking years to reach full size of 8 to 13 feet and half a ton to over a ton depending on sex and individual variation. Everything in the manatee's life happens on extended timelines. Slow growth, slow reproduction, slow tooth replacement, slow movement through water, slow digestion of vegetation. The entire life history calibrated for patience, for persistence across decades, for survival through steadiness rather than speed. The manatee drifting through centuries of evolutionary time, as slowly as it drifts through the water, changing gradually, adapting incrementally, existing now much as it existed thousands of years ago. Slow in body and slow in evolution, conservatism built into every aspect of biology, caution encoded in genes that say, change slowly, move slowly, live slowly. And these instructions have served manatees well enough that they persist despite all the challenges the modern world presents. Though their slowness makes them vulnerable to boats, to habitat loss, to all the rapid changes humans introduce to environments where manatees still move at the same patient pace, their ancestors maintained when the world changed more slowly, and slowness was safer than it has become. The Galapagos tortoise's courtship involves males slowly pursuing females, vocalizing with deep bellowing sounds, and attempting to mount, behaviors that play out over hours or even days as the female slowly walks away and the male slowly follows. persistence eventually overcoming reluctance in interactions that require patience from both participants. After successful mating, females travel to nesting areas, sometimes walking for several days to reach traditional nesting grounds where they dig nests and lay eggs. The eggs incubate for 4 to 8 months, temperature determining the sex of hatchlings. Warmer nests producing more females, cooler nests producing more males. When hatchlings emerge, they face immediate threats from introduced predators like rats, cats, and pigs, predators that evolved elsewhere and to which the tortoises have no natural defenses. Young tortoises that survive grow slowly, adding growth rings to their shells each year, though these rings become less distinct with age and cannot be counted reliably in very old individuals. The tortoises feed on a variety of plants, including cactus pads and fruits, grasses, and leaves. Processing this vegetation through digestive systems, efficient at extracting nutrients from fibrous material. Water comes from vegetation and from occasional pools. The tortoises capable of storing water in their bodies and surviving long periods without drinking, an adaptation to islands where water sources are scarce and seasonal. A Galapagos tortoise might walk the same trails its ancestors walked, moving between feeding areas and resting spots according to patterns established over generations, the paths worn into the landscape by countless tortoise feet. Knowledge of water sources and good grazing passed from parent to offspring not through teaching but through simple accompaniment, young tortoises following adults, and learning through observation what places matter and when to visit them. This slow transmission of knowledge across generations creates cultural continuity in populations, traditions of movement and behavior that persist longer than individual lives. The tortoises collectively remembering their islands in ways that transcend individual memory. Patterns sustained through practice and repetition. Trails maintained through use. The wisdom of place accumulated slowly and preserved carefully in behaviors that change little because change comes slowly to animals who live so long and learn so gradually that new patterns require generations to establish and old patterns require catastrophe to disrupt. The three-toed sloth's muscles contain less protein than the muscles of similar-sized mammals, resulting in reduced strength, but also reduced energy requirements for muscle maintenance. This lower protein content means sloths cannot move quickly even when motivated, as their muscles simply lack the contractile power for rapid movement. The sloth's grip strength remains impressive, despite weak muscles, as the curved claws function like hooks that lock into branches, requiring minimal muscular effort to maintain position. A sloth can hang from a branch while sleeping, or even after death, its claws mechanically locked into place, supporting its weight without active muscle contraction. This locking mechanism allows the sloth to rest completely while remaining securely attached to branches, conserving energy that would otherwise be spent on constant muscular tension. The sloth's skeleton is lighter than other mammals of comparable size, with reduced bone density that decreases weight at the cost of structural strength, another energy-saving adaptation that makes sense for animals that rarely experience impacts or stresses that would require stronger bones. The sloth essentially trades robustness for efficiency, accepting vulnerability to certain types of injury in exchange for lower baseline energy requirements, a trade-off that works because sloths move so slowly and carefully that they rarely fall or collide with objects hard enough to break bones. The sloth's entire body represents a study in energy minimization, every system reduced to barely adequate levels, operating on the principle that adequate is sufficient when energy is scarce, that barely enough is exactly right when leaves provide barely enough calories to live on. The sloth hangs in the canopy, breathing slowly, heart beating slowly, blood circulating slowly, digestion proceeding slowly, all of it calibrated for minimum energy expenditure, for maximum extraction of value from minimal food, for survival in a niche where other animals could not persist, where the energy budget is so tight that only extreme adaptations allow viability. The sloth's slowness, not a choice, but a necessity, not a preference, but a requirement. The only way to make the math work when you eat leaves that should not support mammalian life. Surviving anyway through slowness so profound it redefines what it means to be a mammal, what it means to be alive, what it means to persist when existence itself seems improbable. The Gila monster's venom delivery differs from that of snakes, as the lizard must chew on its victim to allow venom to flow from grooved teeth into the wound, rather than injecting venom through hollow fangs. This chewing process takes time, the Gila monster maintaining its grip and working its jaws slowly to ensure adequate venom delivery, the entire process playing out over minutes, rather than the split-second strikes of venomous snakes. This slow envenomation strategy works for the Gila monster because its prey consists primarily of eggs and helpless young animals that cannot escape during the extended bite, and because the lizard's armor of beaded scales protects it from retaliation during the chewing process. The venom itself is extremely painful, but rarely lethal to humans, serving primarily to deter predators who learn that attacking Gila monsters results in intense suffering. The lizard's warning coloration of black and orange or pink patterns advertises its venomous nature, reducing the frequency of attacks from predators who recognize the pattern and avoid the lizard. When approached by potential threats, the Gila monster typically does not flee, but instead stands its ground, opening its mouth in a threat display that shows the dark interior and warns of the bite to come if the threat persists. This defensive strategy works because the lizard's armor makes it difficult to injure, and its reputation for painful bites makes most predators unwilling to test whether the lizard will follow through on its threat. The Gila monster therefore moves slowly through its desert environment without particular concern for speed, confident in its defenses, unbothered by most other creatures, spending its time searching methodically for food, consuming large meals when it finds them, then retreating underground to digest slowly over weeks or months. The lizard's life consisting of long periods of inactivity, punctuated by brief periods of slow activity, the ratio of rest to motion heavily favoring rest, the lizard spending perhaps 95% of its time underground, emerging only when conditions are suitable and hunger motivates the effort, walking slowly across sand when it does emerge, in no hurry because nothing in its world requires hurry, everything necessary, accomplished through patience, through persistence, through the willingness to search slowly until food is found, to wait quietly until conditions improve, to exist at the pace the desert demands, which is slow during the heat, slower during drought, slowest when both heat and drought combine to make surface activity costly beyond any possible benefit. The koala's specialized diet of eucalyptus leaves means it must carefully select which leaves to eat, as different eucalyptus species, and even different individual trees, vary in toxin content and nutritional value. A koala uses its acute sense of smell to evaluate leaves before eating, sniffing carefully to assess chemical composition, rejecting leaves that contain too many toxins or too few nutrients. This selection process takes time. The koala slowly moving through the tree canopy, smelling leaves, occasionally nibbling to test taste, gradually consuming enough acceptable leaves to fill its stomach. The koala can eat certain eucalyptus species that are toxic to other animals, including humans, because its digestive system contains special bacteria that break down the toxic compounds into forms the koala can tolerate. This ability to process toxic leaves gives koalas access to food that most other herbivores cannot eat, reducing competition and allowing koalas to survive in forests where eucalyptus dominates. However, the digestive process is slow and inefficient, extracting minimal nutrition from the leaves and requiring the koala to spend significant time feeding and even more time resting while digestion proceeds. A koala might spend 4 to 6 hours per day feeding, then 18 to 20 hours resting or sleeping, the long rest periods necessary to conserve energy while the digestive system slowly processes the leaves. The koala's low-energy lifestyle means it rarely engages in social interactions, does not play, does not explore beyond its immediate territory, essentially existing to eat and rest and occasionally reproduce, everything else eliminated as energetically unnecessary. The koala's brain, smaller relative to body size than most mammals, reflects this simplified lifestyle, suggesting that complex behavior and elaborate cognition require energy that koalas cannot spare. The koala's world consists of a few trees, a few pathways between them, knowledge of which leaves are least toxic, and long periods of rest between meals. All of it happening slowly, quietly, with minimal excitement or variation. Life reduced to essentials, and the essentials barely sufficient. Yet koalas persist, hanging in trees, sleeping, waking to feed slowly on leaves, sleeping again, the cycle repeating day after day, year after year. Decades for successful individuals, slowness and simplicity enough to sustain existence in forests of toxic trees, where faster, smarter animals starve or sicken. The koala's specific adaptations, allowing it to occupy a niche that would otherwise remain empty, making a living from leaves that should not support life, succeeding where others fail through specialization so extreme it verges on absurdity. Yet has worked for millions of years, will work for as long as eucalyptus forests remain. The slow loris's toxic bite comes from glands on the inside of its elbows that produce an oily secretion containing allergenic proteins. The loris licks these glands, mixing the secretion with saliva to create a toxic compound that it transfers to its teeth. When threatened, the slow loris can deliver a bite that causes intense pain, swelling, and potential anaphylactic shock in some victims, a defense mechanism that makes most predators reluctant to attack a second time. The loris moves its arms so slowly that it can lick its elbow glands without interrupting its general motion, maintaining its camouflage of stillness in motion while ensuring its bite remains toxic. Mother lorises also lick their babies with the toxic saliva, coating them in the defensive compound to protect them, while the mother forages, the young remaining motionless in tree branches, protected by toxin and stillness, waiting for the mother's slow return. This chemical defense allows the slow loris to maintain its characteristic slow movement without becoming easy prey, the combination of toxicity and camouflage through slowness, creating effective protection despite the loris's small size and apparent vulnerability. The slow loris feeds on tree sap, nectar, insects, and occasionally small vertebrates, food sources that require patient searching and careful approach rather than speed. A loris might spend hours slowly approaching a sleeping bird, moving so gradually that the bird does not detect motion, finally coming close enough to grab the bird before it can wake and flee. This hunting strategy succeeds precisely because of the loris's extreme slowness. Movement so gradual, it does not trigger prey's motion detection systems, approach so patient, it allows complete success rather than rushed failure. The slow loris exists in a temporal framework different from most predators, hunting on timelines measured in hours rather than seconds, succeeding through patience that would exhaust other hunters, maintaining focus across long, slow approaches that end in sudden, brief strikes. The contrast between slow approach and fast strike being crucial to the strategy, the slow part allowing position, the fast part allowing capture, but the slow part taking so much longer and requiring so much more patience that it defines the entire process, shapes the loris's approach to hunting, to moving, to existing in forest canopy, where motion means detection and detection means failure, where only the stillest hunters succeed and the slow loris is stillest of all. The sea cucumber's ability to expel internal organs when stressed, a defense mechanism called evisceration, involves ejecting part or all of its digestive system through either the mouth or the anus, depending on the species and the nature of the threat. These expelled organs can entangle or distract predators while the sea cucumber slowly crawls away, and the organs regenerate over the following weeks or months. This regeneration happens slowly, tissue rebuilding gradually, the sea cucumber surviving without full digestive capacity during the regrowth period, possibly relying on stored energy or reduced metabolic needs. The sea cucumber's ability to regenerate major organs represents an extreme example of the regenerative capabilities many echinoderms possess, trading immediate organ function for long-term survival, accepting weeks or months of reduced capacity in exchange for escaping threats that might otherwise be fatal. This strategy works for the sea cucumber because its lifestyle requires so little energy that it can survive extended periods with reduced or absent digestive function, the animal's slow metabolism, allowing it to wait out the regeneration period without starving. A sea cucumber that eviscerated to escape a predator might spend a month slowly regrowing its digestive system while barely moving, metabolism reduced even below its normally low level, existing in a state of minimal function until regeneration completes and normal activity can resume. This capacity for dramatic regeneration, combined with extreme patience, with willingness to simply wait while body parts regrow, gives sea cucumbers resilience that faster animals cannot match. The ability to survive injuries that would kill creatures dependent on immediate functionality, the slow sea cucumber, outlasting threats through regeneration as slow and patient as its normal lifestyle. Healing measured in weeks, survival measured in ability to reduce needs to nearly nothing and persist anyway, waiting for the body to restore itself, for organs to rebuild, for function to return, all happening at sea cucumber pace, which is to say, slowly, inexorably, patiently, eventually successfully. The sea cucumber's existence, proving that speed is overrated when you can simply wait out problems, when time is abundant and metabolism is negotiable, when survival is measured not in moments of peak performance but in decades of adequate function, interrupted occasionally by necessary repairs that proceed slowly but surely, restoring the animal to slow normalcy, adequate for a life lived at the bottom of the ocean, where fast and slow become meaningless distinctions, and only continuity matters, only persistence, only the slow accumulation of days and years until a lifetime has passed, slowly but completely, at the sea cucumber's own unhurried pace. The giant tortoise's ability to go without water for up to a year comes from several adaptations, including a bladder that can store substantial amounts of water and the ability to reabsorb water from urine and feces before excretion. The tortoise essentially recycles its own water, extracting every possible drop before finally eliminating waste in extremely concentrated form. This water conservation allows the tortoise to survive dry seasons on islands where rainfall is irregular and standing water is rare. During rainy seasons, the tortoise drinks deeply, filling its bladder and tissues with water that will sustain it through months of drought. The tortoise can also derive water from the vegetation it eats, especially succulent plants like cactus, which provide both food and hydration. A giant tortoise might spend months slowly wandering its island, grazing on whatever vegetation is available, its metabolism so slow that it needs very little water to maintain function, its body temperature varying with ambient conditions rather than requiring costly temperature regulation that would demand additional water for evaporative cooling. The tortoise essentially enters a state of reduced activity during dry periods, moving less, eating less, existing in a low-power mode that stretches its water reserves across months. When rain finally comes, the tortoise responds by drinking deeply and increasing activity, taking advantage of the abundance while it lasts, then slowly decreasing activity again as water becomes scarce, the cycle repeating season after season, year after year. The tortoise's long life, allowing it to experience this pattern dozens or hundreds of times, developing a kind of ecological wisdom that is not conscious knowledge but rather appropriate behavioral responses encoded through evolutionary time. The tortoise knowing without knowing that rain will come again, that drought will pass, that patience is rewarded and haste is unnecessary, that survival comes to those who can wait, who can reduce their needs, who can persist through scarcity until abundance returns, as it always does. Eventually, given enough time, and time is what tortoises have, more than almost any other animal. Time measured in years that accumulate into decades, that accumulate into centuries of genetic memory, each generation passing to the next, the adaptations that allow survival in places where water is temporary, but tortoises are permanent, or as permanent as any living thing can be. On islands built by volcanoes that rose from the sea relatively recently in geological time, and will eventually erode back into the ocean, though not in any time frame that matters to tortoises, whose slowness works on ecological timescales but cannot perceive geological change. The tortoises existing in an eternal present, where drought alternates with rain and slowness, remains the appropriate response to both. The thornback cowfish swims through coral reefs at leisurely speeds, its box-like body covered in bony armor plates that make it rigid and ungainly compared to streamlined fish. This body structure sacrifices swimming efficiency for protection, the cowfish accepting reduced speed in exchange for armor that deters most predators. The fish propels itself primarily with its pectoral and dorsal fins, as its rigid body cannot flex to generate the body wave propulsion most fish use. This fin-based swimming produces slow, precise movement that suits the cowfish's feeding strategy of carefully picking small invertebrates from the reef. The cowfish hovers near coral, using its small mouth to blow jets of water at the reef surface, exposing small crabs, worms, and other hidden prey that it then slowly sucks into its mouth. This feeding technique requires precision rather than speed, the cowfish maintaining position with subtle fin adjustments, while it methodically works over each section of reef, missing nothing, rushing nothing, consuming whatever it uncovers, before moving to the next feeding spot. The cowfish's bright coloration warns predators of the toxic mucus it can release from its skin when stressed, a chemical defense that makes eating cowfish dangerous or fatal for predators. This toxicity means the cowfish need not flee from threats, its armor and poison, providing adequate protection without requiring speed. A cowfish might spend hours in the same small area of reef, slowly foraging, occasionally pausing to rest, generally moving at speeds that make its box-like body seem appropriate, anything faster looking ridiculous given its ungainly shape. But the cowfish is not concerned with grace or speed, concerned only with thoroughly working the reef for food, with maintaining position against current, with existing in the slow lane while faster fish rush past. The cowfish, unbothered by the bustle around it, focused on its methodical feeding, its slow progression along the reef, its patient, thorough approach to life, in an environment where many residents rush and hurry, while the cowfish simply continues its slow, steady feeding, proving that speed is optional when you are armored and toxic, and patient enough to extract every available calorie from your environment, through careful attention rather than rapid exploitation. The garden snail's response to danger involves withdrawing into its shell and sealing the opening with a layer of dried mucus called an epiphragm, creating a barrier that protects against predators and environmental stresses. A snail can remain sealed in its shell for weeks or even months during particularly dry or cold periods. Its metabolism reduced to near zero, the animal essentially dormant until conditions improve. This ability to shut down and wait allows snails to survive environments where active animals would perish, the snail's patience outlasting droughts, cold snaps, and other temporary hardships. When conditions improve, the snail dissolves the epiphragm and emerges to resume feeding, moving slowly back into active life. The transition from dormancy to activity is gradual as everything else about snail existence. A snail might cycle through active and dormant periods multiple times per year, responding to seasonal changes by sealing itself away or emerging to feed. Its slow life, punctuated by even slower periods of complete inactivity, the ratio between the two varying with climate and weather. In mild, moist environments, snails remain active most of the year, while in harsh climates they might be active only a few months annually, spending the rest of the time sealed in their shells, waiting for better conditions. This flexibility allows snails to inhabit diverse environments from gardens to deserts, the species adapting its activity patterns to local conditions while maintaining the same basic strategy of slow activity when possible, complete dormancy when necessary. Never rushing, never panicking, simply responding appropriately to whatever conditions exist, closing up to wait out problems, emerging to feed when opportunity arises. The snail's success, built on this ability to be patient beyond most animals' capacity for patience, to wait longer than most creatures can wait, to reduce needs to essentially nothing, and persist in that reduced state until persistence is rewarded, as it usually is. Eventually, the snail's faith in eventually being justified by survival, by the fact that snails exist worldwide, in almost every terrestrial habitat, their slowness, no barrier to ecological success, their patience, no hindrance to reproduction and spread, proving that slowness works if combined with appropriate defensive structures and willingness to simply stop when conditions demand stopping, then start again when starting becomes possible, the cycle continuing across years and generations. Snails slowly inheriting the earth through patience and mucus, and unwillingness to let temporary hardships become permanent failures. The American crocodile basks motionless on riverbanks for hours, conserving energy between feeding opportunities and using the sun to regulate body temperature. This thermoregulation through basking allows the crocodile to maintain functional body temperature without burning calories on metabolic heat production, an energy-saving strategy that suits ambush predators who must occasionally make explosive strikes but spend most of their time waiting. A crocodile might lie completely still for an entire day, occasionally opening its mouth to release heat through evaporative cooling, otherwise appearing more like a log than a living animal, the stillness so complete that birds sometimes perch on the crocodile's back, apparently not recognizing it as a threat. This ability to remain motionless for extended periods allows the crocodile to ambush prey that approaches water's edge. The crocodile erupting from stillness into explosive action, grabbing prey and dragging it underwater before the victim can react. The contrast between the crocodile's patient waiting and sudden strike defines its hunting strategy, but the waiting far exceeds the action in duration, the crocodile spending perhaps 99% of its time motionless, 1% acting, the ratio extreme but effective, each successful strike providing enough energy to support many days of waiting. Young crocodiles feed more frequently on smaller prey, gradually transitioning to the adult strategy of rare large meals as they grow, the shift from frequent small meals to infrequent large meals, tracking the growth in size that makes capturing large prey possible, and makes the energy from such prey sufficient to support extended fasting periods. An adult crocodile can go weeks or even months between meals if necessary, its slow metabolism allowing survival on food intake that would starve mammals of similar size. The crocodile's slowness between hunts is not laziness but efficiency, not weakness but strength. The ability to wait outlasting prey's caution, patience, defeating vigilance through sheer duration. The crocodile willing to wait longer than prey can remain alert, lying still until prey assumes the danger has passed or never existed. The moment of relaxation being the moment of death, the crocodile's patience finally rewarded with a meal that justifies all the waiting, all the stillness, all the hours or days of looking like a log while remaining a predator. The crocodile's life, a study in contrasts, extreme stillness punctuated by extreme violence, slow patience interrupted by fast action. But mostly patience, mostly waiting, mostly the slow breathing and occasional repositioning that characterizes crocodilian existence. Ancient strategy perfected over millions of years. Slowness so successful that crocodilians survived the asteroid impact that killed the dinosaurs, survived ice ages and sea level changes and continental drift, surviving everything through the simple strategy of being patient, being still, being willing to wait as long as waiting takes, then acting decisively when action becomes possible. The waiting and acting both crucial, but the waiting defining the lifestyle, shaping the crocodile's approach to existence, making slowness and patience the foundation on which sudden violence can occasionally be built. The three-toed sloth defecates only once per week, descending from the canopy to the forest floor to deposit feces at the base of the tree where it lives. This weekly journey to the ground represents the most dangerous part of the sloth's life, as ground predators can easily catch the slow-moving animal during its descent and return climb. The sloth typically loses up to 30% of its body weight during defecation, as its slow digestive system allows waste to accumulate for an entire week before being expelled. The reason sloths take this risk, rather than simply dropping feces from the canopy, remains somewhat mysterious, though theories suggest the behavior benefits the trees where sloths live, providing concentrated fertilizer that might improve leaf quality, creating a mutualistic relationship between sloth and tree. The moths that live in sloth fur also benefit from this ground-level defecation, as female moths can leave the fur to lay eggs in the fresh dung, where larvae will develop before emerging as adult moths that fly up to find sloths in the canopy. This complex relationship between sloths, trees, moths, and algae creates an ecosystem centered on the sloth's slow lifestyle, each component depending on the sloth's patient presence and predictable behaviors. The sloth's willingness to risk the dangerous ground visit once per week suggests the benefits outweigh the risks, though from a purely individual survival perspective, the risk seems unnecessarily high, leading some researchers to propose that the behavior is evolutionary holdover from ancestors that lived partly on the ground, now maintained through the moths and algae that have evolved to depend on it, creating reinforcing selection that preserves the behavior despite its dangers. The sloth climbs slowly down the tree trunk, moving with its characteristic deliberate motion even when this slowness makes it vulnerable, reaching the ground and slowly digging a small hole, defecating, covering the feces with leaves, then beginning the slow climb back to safety, the entire process taking an hour or more, time during which the sloth could be easily killed by jaguars, ocelots, or large snakes. Yet the sloth persists in this ritual, performing it weekly throughout its life, surviving through luck, or perhaps through the simple rarity of ground predators, being in the right place at the right time. The sloth's weekly gamble usually succeeding but occasionally failing, evolution accepting the occasional loss as price for whatever benefits the behavior provides. The sloth continuing a pattern older than individual sloths, older than any living sloth, passed down through generations, behavior encoded so deeply it resists change despite danger. The sloth compelled by instinct or biology to make this risky journey, to complete this slow, vulnerable descent and ascent, to maintain this relationship with trees and moths and algae, the entire system built on slowness, on patience, on cycles measured in weeks, everything proceeding at sloth pace, which is slow, but has proven sufficient for survival across millions of years of sloth evolution. Slow but effective, dangerous but survivable. The weekly defecation ritual, just one more example of how the sloth's entire life operates at reduced speed. Even elimination happening only after week-long intervals. The sloth's body, holding waste for durations that would be uncomfortable or impossible for faster animals. Accepting the accumulation because weekly trips to the ground represent appropriate frequency for an animal designed for slowness. For an animal whose entire physiology operates on extended timelines, whose life unfolds at a pace that makes weekly elimination seem reasonable, seem natural, seem like exactly the right interval for a creature that measures time differently than the world around it. The limpet, a marine snail with a cone-shaped shell, clings to rocks in the intertidal zone and feeds by slowly scraping algae from stone surfaces using a ribbon-like tongue called a radula covered in tiny teeth. The limpet moves at speeds even slower than garden snails, traveling perhaps a few inches per hour when actively feeding, often remaining completely motionless for hours or days while clamped tightly to its rock. This clamping provides protection against waves and predators. The the limpet's muscular foot creating suction so strong that attempting to pull a limpet from its rock can break the shell before breaking the seal. Each limpet typically has a home scar on the rock, a depression worn into the stone by the limpet's shell that fits perfectly, providing even better sealing when the limpet returns after feeding excursions. The limpet ventures out to feed when tides cover its rock, scraping algae in slow, methodical patterns, then returns to its home scar before the tide recedes, the return journey guided by chemical trails the limpet left during its outward journey. This navigation happens slowly and precisely, the limpet never straying far from its home location, foraging in a small area it knows intimately, returning always to the same spot, the same scar, the same precise position where its shell fits the rock perfectly. A limpet might occupy the same home scar for years, gradually deepening it through the constant abrasion of its shell, the rock and limpet slowly wearing each other into perfect complementary shapes, a relationship built through patience and repetition, through thousands of feeding excursions and returns, through the slow accumulation of tiny movements that add up to substantial effects over time. The limpet's life consists of waiting for tides, scraping algae, returning home, waiting again, the cycle repeating twice daily with the tidal rhythm, the limpet's slow movement perfectly matched to the slow but predictable changes in water level. The animal's entire existence structured around tidal timing that operates on scales much larger than individual limpet lives. Ancient patterns that limpets follow without understanding, responding to water, presence and absence with appropriate behaviors. Feeding when submerged, waiting when exposed, surviving through patience and tight sealing, and the willingness to live in one tiny area of rock for an entire lifetime. The limpet's world, measured in inches, experienced at speeds that make progress invisible, yet complete in ways that larger ranges could not improve. The limpet, finding everything it needs within a few feet of its home scar, requiring nothing more than what this small space provides, proving that range is less important than thorough knowledge of limited space. That moving slowly through a small area can support a full life if the area is well chosen and thoroughly utilized. The limpet's strategy working for millions of years. These slow grazers, persisting on rocks worldwide, each individual slowly scraping its algae, slowly returning home, slowly living out its years in patient devotion to a single spot of stone in an ocean of possibilities, choosing depth over breadth, intimacy over exploration, stillness over wandering. The limpet's choice or instinct or evolutionary programming, keeping it close to home, keeping it slow, keeping it alive, through strategies that faster animals might not appreciate but cannot deny the effectiveness of the limpets persisting, slowly, patiently, clamped to their rocks, like tiny monuments, to the power of staying put. The pygmy three-toed sloth lives only on a single small island off Panama, moving even more slowly than mainland sloths, and living a life so sedentary that algae and fungi grow thicker in its fur than in any other sloth species. These island sloths feed almost exclusively on the leaves of red mangrove trees, an even more restricted diet than mainland sloths, and they spend much of their time in mangrove branches hanging directly over water. The island environment apparently relaxed, selection pressures that might otherwise require faster movement or more diverse diet, allowing the pygmy sloth to become even more specialized, even slower, even more limited in behavior than its mainland relatives. The population numbers only a few hundred individuals, all living within a few square miles of mangrove forest, the entire species confined to one small island, moving slowly through trees that grow at the edge of water, occasionally swimming between mangrove patches with slow, deliberate strokes. The swimming, perhaps the closest the pygmy sloth comes to rapid movement, though even its swimming qualifies as leisurely by most standards. The species faces extinction risk from any significant disruption to its tiny habitat. The extreme specialization that allowed it to thrive on this one island, also making it vulnerable to changes that mainland sloths with broader ranges and more flexible diets could survive. The pygmy sloth represents an endpoint of sloth evolution. Slowness taken to its absolute limit. Specialization refined until the animal can survive in only one place, eating one type of leaf, moving even less than animals already famous for barely moving. The pygmy sloth existing at the far edge of what slowness can accomplish, teetering on the boundary between viable population and extinction, persisting in its small refuge through the same patience that characterizes all sloths, but expressed in even more extreme form. Slower growth, slower movement, slower everything. The pygmy sloth's entire existence playing out at the absolute minimum pace that still qualifies as living, barely faster than the trees it inhabits, approaching plant-like stillness while retaining animal nature, proving that slowness has almost no lower limit if environment permits, that animals can slow down nearly to the point of immobility and still survive if their habitat provides everything they need within reach. The pygmy sloth reaching out slowly to grab mangrove leaves, chewing slowly, digesting slowly, moving to the next branch slowly, existing slowly in its island paradise, oblivious to its precarious status, unconcerned with the fact that its entire species could disappear if the island's mangroves were destroyed, living now as its ancestors lived, slowly and simply, in the only place on Earth where such extreme slowness works, where specialization so narrow permits survival. The island's isolation protecting the pygmy sloth from competition and predation that might otherwise eliminate such an extreme specialist. Allowing this experiment in slowness to continue, at least for now, the future uncertain but the present slow and adequate. The pygmy sloth hanging in ITS mangroves, covered in algae, moving barely at all, alive in the most minimal sense, yet alive nonetheless, slow but sufficient, specialized but successful within its narrow context, proof that evolution can push slowness to extraordinary extremes when circumstances allow, when the environment provides enough support that barely moving suffices, when patience reaches its logical conclusion and animals become almost indistinguishable from the plants they eat, almost but not quite, the pygmy sloth retaining just enough activity, just enough movement, just enough animal nature to remain an animal. Though an animal so slow, it redefines the category, pushing the boundaries of what animal means, showing that the line between animal and plant blurs at the extreme end of slowness. The pygmy sloth living in that blurred space, slow beyond most animals' capacity for slowness, patient beyond most creatures' ability to be patient, surviving in its unique way, in its unique place, irreplaceable and wonderful and desperately vulnerable, a small miracle of evolution hanging slowly from mangrove branches, existing at the edge of existence, slow at the edge of stopping, moving at the edge of stillness, alive at the edge of life. The horseshoe crab walks across ocean floors, using 5 pairs of legs, each pair moving in coordinated sequence that produces forward progress at speeds rarely exceeding 0.3 miles per hour. These ancient arthropods, which are more closely related to spiders than to true crabs, have remained essentially unchanged for 450 million years, their body plan so successful that evolution found no reason to modify it across hundreds of millions of years of environmental change. The horseshoe crab's slowness serves it well, as it feeds on worms, mollusks, and other invertebrates buried in sediment, prey that does not require speed to catch. The crab plows slowly through sand and mud, using specialized appendages near its mouth to manipulate food and push it into its grinding mouthparts. A horseshoe crab might spend an entire night slowly crossing a small area of sea floor, feeding as it goes, processing sediment to extract edible material, its progress measured in yards over hours, its path marked by a shallow furrow where it disturbed the bottom. During breeding season, horseshoe crabs migrate to beaches where thousands gather during high tides, females coming ashore to lay eggs, while males compete to fertilize them. The beaches briefly becoming covered with slowly crawling horseshoe crabs, in numbers that turn the sand dark with their bodies. After breeding, The crabs slowly return to deeper water, leaving behind eggs that will develop in the sand, eventually hatching into larvae that will spend years growing slowly through multiple molts before reaching adult size. A horseshoe crab might live 20 years or more, growing slowly throughout its life, adding size with each molt, accumulating age and experience at the same patient pace. It accumulates distance traveled, the crab's entire existence, measured in slow increments, slow growth, slow movement, slow feeding, slow reproduction, everything proceeding at a pace that seems impossibly leisurely, yet has proven adequate for longer than most animal lineages have existed. The horseshoe crab's slowness is not a disadvantage but a feature, not a limitation but an adaptation, part of a survival strategy so successful it has persisted essentially unchanged since before dinosaurs existed, since before most modern animal groups evolved. The horseshoe crab walking slowly through hundreds of millions of years of Earth history, surviving mass extinctions, surviving climate changes, surviving the rise and fall of countless other species. Still here, still slow, still walking the ocean floor in the same patient manner its ancestors used when the world was young and strange. The horseshoe crab carrying within its body a message about the power of slowness, about the value of not changing when change is unnecessary, about the success that comes from finding a strategy that works and maintaining it regardless of what else happens in the world around you. The horseshoe crab's existence validating patience on geological timescales, proving that slow and steady does not just win races, but survives epochs. The crab's ancient form, walking slowly into the future, carrying the past in its unchanged body, living proof that sometimes the best response to a changing world is to remain the same, to keep walking slowly, regardless of what rushes past, to trust that the pace which worked for 450 million years will continue working, that slowness is not obsolescence, but persistence, that ancient does not mean outdated, that crawling patiently through the ages is its own form of success, perhaps the ultimate success, outlasting everything through the simple strategy of continuing, slowly, patiently, one deliberate step after another, across millions of years and countless generations. The horseshoe crab slow but eternal, patient but persistent, ancient but very much alive. The garden slug, similar to snails but lacking an external shell, moves at comparable speeds to snails, but faces greater vulnerability to drying out without the protective shell to retreat into. This vulnerability means slugs are even more restricted to damp environments and nighttime activity than snails, emerging to feed only when conditions are sufficiently moist to prevent dehydration. A slug must produce even more mucus than a snail relative to body size, as the mucus provides not only locomotion but also some protection against moisture loss, coating the slug's body in a slippery layer that reduces evaporation. This increased mucus production requires significant resources, energy, and materials that slugs must obtain from food, meaning they must feed efficiently to maintain the mucus supply necessary for movement and survival. Slugs feed on a wide variety of plant material, fungi, and decaying organic matter. Their varied diet allowing them to find food in most environments where moisture permits their activity. A slug might spend an entire night slowly crossing a garden, grazing on leaves and seedlings, leaving a trail of mucus that marks its path and consumes resources the slug must replace through feeding. The slug's lack of shell means it can squeeze through smaller openings than snails, accessing food sources in tight spaces, but also means it lacks the defensive option of withdrawing completely from threats. Instead, slugs rely on distasteful mucus to deter predators, some species producing particularly noxious secretions that cause mouth numbness or irritation in animals that attempt to eat them. The slug's slow movement makes it vulnerable to predators, despite its chemical defenses, as many predators have evolved tolerance to slug mucus or methods of consuming slugs that bypass the defensive slime. Birds can wipe slugs on grass to remove mucus before eating them, and some beetles inject digestive enzymes into slugs to liquefy their internal organs, then drink the resulting fluid, bypassing the protective external slime entirely. Despite these vulnerabilities, slugs persist worldwide. Their slow, patient approach to life, sufficient to maintain populations even in the face of substantial predation pressure, the slug's high reproductive output compensating for individual losses. Each slug capable of laying dozens or hundreds of eggs when conditions are suitable, the next generation slowly emerging to begin their own slow lives, crawling through gardens and forests at the same patient pace their parents used, leaving the same mucus trails, facing the same dangers, persisting through the same strategy of patient feeding, careful moisture management, and sufficient reproduction to outlast predation. The slug's slowness, not preventing success, but rather being part of a successful strategy that balances vulnerabilities with adaptations, accepting that some individuals will be lost, but ensuring that enough survive to continue the lineage. Generation after generation of slow gastropods moving through the world, making their mucus trails, eating their food, living their slow lives in the damp places where shells are unnecessary and patient grazing suffices to support existence. C. The slug proving that even without protective structures, slowness works if combined with appropriate behaviors and sufficient fecundity. The slow, outlasting the fast through patient reproduction and tolerance for individual loss. Populations persisting even as individuals fall to predators. The species continuing even as specific slugs end, the pattern repeating across years and places. Slugs slowly inheriting every moist environment through persistence and patience, and the willingness to keep trying, keep sliding forward on mucus trails, keep living slowly despite dangers. The slug's existence confirming that protection comes in many forms, and slowness need not depend on armor if other adaptations suffice. If distasteful mucus and flexible bodies and high reproduction rates provide enough advantage that slowness remains viable, remains sufficient, remains a successful strategy for existence, even in a world full of creatures faster and fiercer and apparently more capable than the humble garden slug, slowly crossing the wet grass at night. The West Indian manatee communicates with others of its kind through a variety of vocalizations, including squeaks, squeals, and chirps, sounds produced slowly and rarely, compared to more vocal marine mammals like dolphins. Manatees are generally solitary animals, coming together primarily to mate or to gather at warm water refuges during cold weather, their social interactions infrequent and brief, consisting mainly of gentle touching and occasional vocalizations. A mother and calf maintain closer bonds, the calf staying with its mother for up to 2 years, learning through observation where to find food, where warm water exists during winter, and how to navigate the waterways that will become its home range. This extended childhood happens slowly, the calf growing gradually, learning patiently, never rushed. The mother tolerant of the calf's presence for years before finally encouraging independence. Manatee social structure reflects their slow lifestyle. No complex hierarchies, no competitive interactions, just individuals occasionally sharing space when resources concentrate, tolerating each other's presence without conflict, sometimes engaging in gentle play, but mostly simply existing in parallel. Each manatee focused on its own feeding and breathing, and slow progression through the water. The manatee's gentle nature extends even to aggressive interactions, which consist mainly of displacement rather than violence. A larger manatee simply moving into space occupied by a smaller one, the smaller individual slowly moving aside. No fighting, no injury. Conflicts resolved through minimal effort and acceptance of size advantage. The manatees apparently content to avoid confrontation, to coexist peacefully, to share warm water refuges during winter, even as dozens or hundreds gather in small springs and canals. The concentration unusually high, but the interactions remaining calm, manatees resting in close proximity, but each maintaining individual space, occasional contact accepted but not sought. The gathered animals waiting out the cold weather in the warmth of spring-fed water, slowly feeding on whatever aquatic vegetation grows nearby, mostly resting, conserving energy until temperatures rise, and they can disperse back to their individual ranges. The manatee's slow, peaceful lifestyle seems almost idealized. A mammalian existence free from the competitive pressures that drive most animals to constant activity and interaction. The manatees instead, living independently, moving slowly, feeding constantly but without urgency, avoiding conflict, tolerating presence of others when necessary, preferring solitude when possible, the entire social system based on low-key coexistence rather than complex relationships. The manatees' interactions, as slow and gentle as their movements. Communication minimal, because communication is rarely necessary when each individual minds its own business and resources are sufficient. That competition is unnecessary. The manatee's gentle nature, perhaps resulting from this lack of competition, from the abundance of aquatic vegetation and the absence of serious predators in their range. Conditions that allow the manatees to simply exist peacefully, slowly grazing and drifting and breathing, living out their long lives without drama or urgency, embodying a kind of aquatic tranquility that makes them symbols of peace and gentleness. Representations of what life might be like without competition or fear, though of course the reality is that manatees do face threats and do compete for warm water access during extreme cold. But these stresses remain mild compared to what most animals experience, allowing the manatee to maintain its slow, gentle approach to existence, its patient processing of endless vegetation, its calm acceptance of other manatees when they share space, its peaceful progression through waters that support this gentle giant, this slow herbivore, this calm presence in coastal waters and rivers where manatees have drifted for millions of years, adapting slowly, changing gradually, maintaining always their characteristic patience, their slowness, their gentle approach to life, in an ocean that can be violent, but for manatees is mostly calm, mostly supportive, mostly sufficient to allow slow living and patient grazing and peaceful coexistence with the few others of their kind they encounter in their slow journeys through warm waters. The Gila monster's slow metabolism allows it to survive on just 3 or 4 large meals per year, each meal providing enough energy to sustain the lizard through months of inactivity. This extreme fasting ability results from several adaptations, including the fat storage in the tail, which swells when the lizard is well fed, and shrinks during fasting periods as the stored fat is metabolized. The lizard's slow metabolic rate means it burns energy very gradually. A full tail, providing sufficient calories to sustain basic functions for many weeks or months. The Gila monster spends this fasting time underground in burrows, maintaining stable temperature and humidity, avoiding the energy costs of surface activity, essentially entering a state of reduced function that borders on dormancy, though the lizard remains capable of emerging if conditions warrant. This ability to simply wait underground for months requires extraordinary patience, or perhaps, more accurately, requires no patience at all, if patience implies active waiting rather than simply existing in a reduced state until external conditions or internal hunger prompts activity. The Gila monster does not count days or anticipate meals, simply exists until existence requires action, then acts slowly and deliberately, searching for food with the confidence that food exists somewhere, and patient searching will eventually locate it, the search itself unhurried, because rushing uses energy, and energy is the resource the Gila monster must conserve above all else. When the lizard does find food, whether eggs in a nest or young animals in a burrow, it feeds slowly and thoroughly, consuming everything available, maximizing the energy gained from the opportunity, then returning underground to begin another long period of waiting. This feast or famine lifestyle operates on timelines that make other animals' seasonal patterns seem rushed. The Gila monster, measuring time between meals in months, measuring active periods in days or weeks, separated by months of inactivity. The entire year, consisting mainly of underground waiting, punctuated by brief surface appearances when temperature and humidity and hunger align to make activity worthwhile. The lizard's life consists more of not living than living, if living means activity and interaction with the environment. Yet the Gila monster is fully alive even when buried underground doing nothing. Alive in the sense that its body maintains itself, that its cells continue functioning at minimal levels, that it retains the capacity to emerge and feed when appropriate, that it persists across years and decades through this pattern of long waits and brief activities, surviving through patience taken to extremes that make other patient animals seem impatient by comparison. The Gila monster's slowness extending beyond movement into lifestyle, into annual patterns, into a commitment to inactivity so profound, it defines the species, shapes its appearance, determines its range, limits its distribution to environments where underground retreats provide adequate shelter and surface conditions permit at least occasional feeding opportunities, the desert providing exactly this combination, harsh enough that activity is costly, stable enough that waiting underground works, productive enough during certain periods that food can be found when needed. The Gila monster perfectly suited to this environment, specialized for patience, adapted for waiting, designed for slowness in both movement and lifestyle, the entire organism optimized for doing as little as possible, as slowly as possible, while still maintaining viability. The Gila monster existing at the edge of active animal life, bordering on plant-like persistence, remaining animal through its ability to move when necessary, but spending so much time not moving that the distinction blurs. The lizard's life, a testament to the power of patience, to the success that comes from accepting that most of life involves waiting and only brief moments require action. The Gila monster embracing this reality, building a survival strategy from patience, thriving through slowness, persisting through its willingness to do nothing for longer than most animals can imagine, then finally, slowly, emerging to feed before returning to its burrow to wait again, the cycle repeating. Slow and patient, and perfectly suited to the desert's slow and patient rhythms. The Galapagos tortoises population on different islands evolved distinct characteristics based on local conditions, creating subspecies that differ in size, shell shape, and behavior despite being closely related and interfacing recently in evolutionary time. The variations arose because each island presented slightly different challenges, different food available at different heights, different terrain requiring different mobility, different climates imposing different water needs. The tortoises adapted slowly, populations isolated on their separate islands for thousands of generations, each generation slightly better suited to local conditions, differences accumulating gradually until they became noticeable, eventually becoming substantial. The changes happening so slowly that no individual tortoise ever experienced change, just lived in conditions its ancestors lived in, already adapted, already suited, the change visible only when comparing populations across islands or when examining fossils that show the slow progression from ancestral form to modern varieties. This pattern of slow divergence in isolation demonstrates how evolution operates on patient timelines, how change accumulates through slight advantages maintained across countless generations, how slowness characterizes not just the tortoise's movement, but their evolutionary trajectory, everything about them changing gradually or not at all. The pattern of slow adaptation, producing slow animals perfectly suited to islands where slowness works, where being slightly better at reaching high leaves, or being slightly more efficient at storing water, or being slightly more mobile across rough terrain, translates to reproductive advantage. Subtle enough that individual advantage is negligible, but population-level effect is substantial given enough time. And time is what island tortoises had. Thousands of years of isolation, thousands of generations of slow change, producing eventually the variety we see today. Each island's population distinct, each tortoise carrying in its shell, shape and leg length and neck flexibility, the history of its lineage's slow adaptation to specific conditions. The tortoise itself, unaware of this history, unconcerned with evolution, simply eating and resting and occasionally reproducing, following patterns encoded in genes that were shaped by selection so gradual, no individual ever perceived it. The tortoise existing now as the product of ancient slowness, its body shaped by patient evolutionary processes, its behavior determined by genes refined through slow testing against environmental conditions, everything about the tortoise, the result of slow causes, producing slow effects. Evolution at tortoise pace, producing animals that move at tortoise pace, the circularity seeming almost intentional, though it is simply how things worked out when slow-breeding animals, with long generations adapted to island environments over thousands of years, the slowness reinforcing itself. Slow generation time, meaning slow evolution, meaning adaptations for slowness. Being preserved because rapid adaptations were unnecessary and possibly detrimental on islands where food was adequate and predators were absent, and the successful strategy was simply continuing what worked, which was moving slowly, eating slowly, living slowly, reproducing slowly. The tortoises' slowness, proven successful by their persistence, by their diversity, by their occupation of multiple islands, each requiring slight variations on the same slow theme. The Galapagos tortoises existing as proof that slowness is not just viable, but productive, when given enough time, enough isolation, enough stability to allow patient processes to work their gradual magic, shaping bodies, shaping behaviors, shaping entire lineages of animals who carry within themselves the accumulated wisdom of thousands of generations of slow living, slow adaptation, slow success in environments that reward patience above all else. The nautilus, a cephalopod related to octopuses and squid, moves through ocean waters by jet propulsion, expelling water from its body cavity to push itself backward at speeds around 2 feet per second when active, though it spends much time drifting or resting motionless. This movement, while faster than the slowest animals, is remarkably slow for a cephalopod, as squids and octopuses are generally known for rapid movement and quick strikes. The nautilus's slowness results from its chambered shell, a beautiful spiral structure that provides buoyancy but creates drag, making rapid swimming energetically expensive. The nautilus uses this shell to control its depth, adjusting gas content in the chambers to become more or less buoyant, allowing slow vertical movement through the water column without swimming effort. The nautilus feeds on crustaceans, fish, and carrion, capturing prey with dozens of tentacles that lack the suckers of its squid and octopus relatives. The nautilus hunts at night, rising from deep water to reef areas where it searches slowly for food, using excellent senses of smell to locate prey in darkness. The nautilus's eyes are simple, lacking lenses and functioning more like pinhole cameras, providing crude images adequate for detecting movement and shapes, but not detailed vision. This limited vision suits the nautilus's slow hunting style, relying more on smell than sight. Approaching prey slowly once detected, tentacles extended, capturing whatever comes within reach. The nautilus's slow lifestyle includes slow reproduction, females laying eggs that take up to a year to hatch, producing just a few offspring per year, each one a miniature version of the adult, complete with small chambered shell. Young nautiluses grow slowly, adding chambers to their shells gradually, taking years to reach full size, living potentially for 20 years or more. Slow maturity, matching slow growth, matching slow movement. Everything about the nautilus operating at reduced pace compared to its cephalopod relatives. The nautilus, existing as a living fossil, its body plan essentially unchanged for hundreds of millions of years. One of the oldest living animal designs, persisting through the same strategy that worked when the seas were young. Slow hunting, slow growth, slow reproduction, slow movement, all of it adequate when you carry a shell that protects you from most threats, and live in deep water where competition is reduced and prey is available to those patient enough to search for it. The nautilus, drifting through the darkness, beautiful spiral shell, glowing faintly when caught by bioluminescent flashes from other deep-sea creatures, tentacles trailing, body oriented downward as it descends after a night of slow hunting, returning to deeper water where it will spend the day resting, conserving energy, existing in patient stillness until night returns and hunger prompts another slow ascent, another slow search for food, the cycle repeating night after night, year after year. The Nautilus's life unfolding at the same patient pace. Its ancestors maintained hundreds of millions of years ago. Slowness so successful, it never required modification. The Nautilus, swimming slowly into the future, carrying the distant past in its unchanged form, living proof that some solutions work forever if the problems they solve remain constant. That slowness is not just viable, but can be optimal when conditions favor patience. When rushing confers no advantage, and steady presence suffices. The Nautilus embodying this truth, demonstrating through its continued existence that ancient and slow and simple can outlast modern and fast and complex. That survival goes not to the quickest or the cleverest, but to the adequately adapted. And the Nautilus is adequate, has been adequate for longer than most lineages have existed, remains adequate now, drifting slowly through dark water, hunting slowly, living slowly, persisting slowly through time that measures itself in ages, while the Nautilus measures itself in breaths, in tentacle movements, in slow jets of water expelled from its shell, propelling it backward at speeds that barely qualify as motion, yet motion sufficient for the Nautilus, adequate for its needs, enough to sustain a lineage across epochs. The slow Nautilus outlasting countless faster creatures. Patience, triumphant over speed. The spiral shell, beautiful and ancient and perfect, containing within its chambers the secret of success across geological time. And the secret is simply this, that being slow enough, being patient enough, being simple enough, allows survival when complexity fails, and speed exhausts itself, and the only animals remaining are those who never rushed, who never panicked, who simply continued at their own slow pace regardless of what happened around them. The Nautilus, knowing nothing of this philosophy but living it completely, being the embodiment of patient persistence, the living symbol of slowness as successful strategy. The ancient cephalopod, swimming slowly backward into the future, carrying the past within its shell. Both fossil and living creature, both ancient and modern, both slow and successful. Proof that these qualities need not conflict, that slowness and success not only can coexist, but have coexisted for hundreds of millions of years, and may coexist for hundreds of millions more, if the ocean permits, if conditions remain suitable, if the Nautilus can continue its slow existence in waters that support slow living, slow hunting, slow everything that makes the Nautilus what it is, has been, and hopefully will continue to be. Slow survivor in an ocean of change, ancient form in modern seas, patient creature in an impatient world. The Nautilus drifting, always drifting, slowly through the dark. And now the slowest creatures fade behind your thoughts. We've drifted through 100 quiet truths about nature's most patient animals. From sloths hanging in rainforest canopies to limpets clinging to tidal rocks. From manatees grazing in warm waters to horseshoe crabs walking across ancient seafloors, you are connected to this world. The same patience that allows a sloth to survive on toxic leaves, the same persistence that carries a tortoise through a century, exists within you too. The ability to slow down, to move at your own pace, to trust that patient progress reaches destinations just as surely as rushing. Tonight, as you rest, three-toed sloths hang motionless in the darkness. Garden snails leave their silver trails across wet leaves, and giant tortoises sleep in their island homes, their slow breathing matching the rhythm of ancient time. The slow creatures continue their patient lives, measuring progress in ways that have nothing to do with speed, succeeding through strategies that have worked for millions of years. And you are safe, warm, resting in a world full of wonder, a world where slowness is not weakness but wisdom, where patience is not passive but powerful, where the steady and the gradual inherit the earth through the simple act of continuing, slowly, surely, persistently. If you're still awake, go ahead and watch the next chapter. Sleep well and dream softly of creatures who move through life at their own unhurried pace, who prove that there is no single correct speed for existence, who show us that sometimes the slowest path is the surest path, that patience rewards those who practice it, that slowness is its own form of grace. Dream of silver snail trails and tortoise patience, of manatees drifting and sloths hanging still, of all the slow and gentle creatures who share our world, moving at speeds we've forgotten are possible, teaching lessons we've forgotten to hear, existing in ways that remind us that life need not be rushed, that presence matters more than progress, that being here slowly is better than rushing elsewhere, that rest is not failure but wisdom, that stopping is not giving up but gathering strength, that slow, patient, gentle living is not just acceptable but admirable, not just viable but valuable, not just possible but perfect in its own quiet way. Good night.